Today we will be talking about asymptotic complexity. So what is asymptotic complexity? Asymptotic complexity is to describe the limiting behavior of an algorithm. What is limiting behavior? Limiting behavior means the boundary of the execution. The boundary of execution, the boundary could be of two types. One is time and another is space. So the complexity would be time complexity and space complexity. Another definition of asymptotic complexity says it is to evaluate the performance of an algorithm in terms of input. That means, given an input, what can we deduce about the total amount of time and space it would take to generate the result? Asymptotic complexity is generally of three types. The first one is big O. Big O notation is about worst case asymptotic complexity. This is to give the least upper bound. What is least upper bound or the tightest upper bound? That means how much time, how much max time and space an algorithm will take to generate the output. So if we take it on the graph, we see that there is a function fn and there is another function gn, and gn consistently after point n naught remains higher than fn. So fn is always less than or equal to cgn, where c is a constant and n naught is another constant. C greater than 0 and n naught greater than or equal to 1. In this case, the big O notation would be written as f of n is equal to O of g of n. So g of n would give tightest or the least upper bound for f of n. If we take it with the help of example, we see here that f of n is equal to 3n plus 2. Now, what should we take c such that the g of n and c becomes greater than f of n? If we take c is equal to 4, then c g of n like this becomes 4n, and 4n is greater than 3n plus 2 always. That means 4n gives a tightest upper bound for f of n, and then 4n can be written as like this. Now we should take care of this while writing any asymptotic complexity. We always take care of variables and just discard the constant part of it. Hence this will be finally written as O of n. Now moving to the second type of asymptotic complexity, and that would be big omega, which gives us best case representation, that is the biggest lower bound. What is the least amount of time a program or an algorithm basically would take to produce the output? If we take it on the graph, we see here the constant and gn is consistently lower than the function after point n naught. So f of n is always greater than or equal to c gn, c being greater than 0 and n being greater than or equal to 1. In such cases, the g of n will give the biggest lower bound for f of n, which would be written as big omega. If we take it with the help of example, say f of n is 3n plus 2, what should we take our g of n such that it always remain lesser than f of n? That would be 3 of n. Hence, if we write it as omega, it will go like this. Now, as I said, while taking asymptotic complexity, we just discard the constant part and take only the variable part. it will finally be written as like this. The third type of complexity asymptotic notation is theta notation, which gives us an average case. So here we see that f of n is bounded by two different functions, c1 gn and c2 gn, which can be written as here g of n and g of n, c1 and c2, they are giving higher and lower bound for f of n. So f of n is describing what it would take an algorithm to perform in an average time and space complexity. Now let us look at some of the examples for time complexity, and first just take iterative examples, and let's understand how to calculate the complexity. For example, if we have a function like this, I is an integer and which is used to run a loop from 1 to n, that means n times, and within the loop we are just doing some constant operation. For example, if we are printing something, constant operation, constant time operation, that means if we are to take the time complexity, we look at how many times this iterative for loop is performing, that is n times, and each time it is doing some constant operation, which can be written as n into O of 1, and this can again be written as O of n into 1, and we always take the variable part, hence the actual time complexity would come out as O of n. Now if we look at the second example, again we have a function and we are having two different loops. We are having one integer I and another integer j, then we have one loop for I from 1 to n, and then another for loop for I 1 to n, and then we are again doing some constant time operation. So here we are seeing that the outer loop is running n times, and then the inner loop is again running n times. So the total number of times the constant operation is running is n into n times, that is n square times, and this would be our time complexity. Let's look at third example. If we are having one function a and then I is equal to 1, and for the for loop where the I is equal to 1 and I square is less than or equal to n, and then I plus plus, and we are doing some constant operation. So we will look at in the iteration how the value of I is being impacted with the value of n. So if the value of n is 1, I run 1 times. If the value of n is 2, I runs 1 time. If the value of n is 2, if the value of n is 4, I runs 2 times. If the value of n is 16, I runs 4 times. And similarly, if the value of n is n, I runs under root n times. That means the total number of time this iteration will run is underscore n times. Hence, that would be our time complexity. Now, let's take an example of iterative approach and see how the Oh, let's take an example for recursive approach and see how the time complexity would be calculated. So if we take a function, if we take an algorithm to calculate Fibonacci, so that would be something like this. If n is equal to 1, then we just return n. Else, we again call the Fibonacci. So here we are seeing that the Fibonacci function for n is calling two different types, two different functions. So each time, and they again will call two different function calls. So each time we are having two different function calls, and that would go n times in the worst case, because hence the complexity would go exponential. So we see that in recursive approach the complexity could be exponential. So here we saw that a recursive approach to solve any function would result in exponential time complexity, might result in exponential time complexity if we do not take any other measure. Apart from these, we also have something called a recursive equation, which is also used to find out the time complexity of a recursive function. For example, for Fibonacci, the recursive equation would look like this. Now, when we solve this, we will eventually come out as 2 to the power n. To solve these complex equations, we usually use something called Master's theorem. About which we will talk in certain coming lectures. Now, let's look at space complexity and how to calculate it. Again, first talking about iterative functions. If we take an example where we are not taking any more space apart from what has already been provided. So for example, if we are given a function, if we are given some function and we are given an int array, and we are just iterating over the array, here what we saw that we are not taking any more, not taking any extra space. Hence, we are using only constant space complexity, that would be written as O of 1. Instead of this, if we would have been taking some space apart from what is already been provided to us, for example, if an array is provided to us but we are again making another array, and then we are just trying to initialize it. Here we are taking n extra space. Hence the complexity would be O of n. This was the case for iterative function. Now let's look at recursive functions. So in iterative function, what we saw that if we do not take any extra space, then the complexity would be O of 1. But if we take some, then the complexity would go higher accordingly. But that is not the case with the recursive function. In recursive function, we have something called recursive stack, which is used to keep all the active call stacks. And in the worst case, size of the stack would be our complexity, because even if we are not taking any other memory allocation apart from what has been provided to us, the recursion in itself implicitly would be taking some space. Let's understand this with an example. If we have a function a, and then if the function works like this, the function calls itself again and again here. What we are seeing that the function is calling itself again and again, and after that it is printing something. So the recursion would something look like this. It is calling itself and printing something, calling itself and then printing something. So this would go n times. If our n would have been 3, it would have looked something like this. And this is our recursion tree. If we look at in the recursion stack, the active call stack would something look like this. And this will call this a of 2, which will call a of 1, which will call a of 0, and when it will start returning, then it will return like this. Then it will call the main function. Hence, at any given point of time, it is taking n plus 1 space maximum. Hence, our space complexity would go n plus 1. That would be O of n. So we saw that in recursive function, even if we do not take any memory allocation explicitly, implicitly the recursive function would have been taking some space in form of recursive stack. Thank you.